Good day everyone. So now our discussion is all about relations, abelian group, symmetries, and group of permutation. But before that, let's have first our learning objectives. At the end of the lesson, the student should be able to define what is relations, abelian group, and symmetry. Determine what are the types of relations. Appreciate the concept of abelian group. Illustrate the symmetries and groups of permutation. And apply relations and permutation in real-life setting. So first, we are going to discuss about relations. So what is relations? Relations will be defined in terms of ordered pairs A, B of elements where A is designated as the first element and B as the second element. Specifically, the set of ordered pairs AB is equal to the set of ordered pairs C, D if and only if A is equal to C and B is equals to D. In particular, the set of ordered pairs A, B is not equal to B, A unless A is equals to B. So we have the Cartesian product. Let A and B, the two sets, the product set or Cartesian product of A and B, written A cross B. And read as A cross B is the set of all ordered pairs AB such that A is an element of set A and B is an element of set B. Namely, A cross B is a set of ordered pairs A, B such that A is an element of set A and B is an element of set B. So let's have an example. So let A is a set consists of these elements 1, 2, 3. And B is a set consists of these elements 0, 1, 2, 4. So find A cross B and A squared. So now we have to find A cross B. So let's answer. A cross B must be the set which consists of these all ordered pairs. So our first element belongs to set A and our second element belongs to set B. So, and you can clearly see our ordered pairs which are 1, 0, 1, 1, 1, 2, 1, 4, 2, 0, 2, 1, 2, 2, 2, 4, 3, 0, 3, 1, 3, 2, 3, 4. These are all the ordered pairs inside A cross B. So what if we answer B cross A? So while in getting our B cross A, the ordered pairs in the first element belongs to set B and the second element belongs to set A. So let's have A squared. So let's answer. So in getting our A squared, we only focus on our set A because it is A squared, which consists of these elements 1, 1, 1, 2, 1, 3, 2, 2, 2, 1, 2, 3, 3, 3, 3, 1, 3, 2. So A squared must be this set which consists of these all ordered pairs. When we talk about product sets, in general, the concept of a product set can be extended to more than two sets in a natural way. So the Cartesian products of set A, B, and C, denoted by A cross B, cross C, consist of all ordered pairs A, B, C, where A is an element of set A and B is an element of set B and C is an element of set C. So now, let's have an exercises. Let H is a set which consists of this element. Mark Joy. I is the set which consists of these elements. K, J, Fur. And J is the set which consists of this element, Daniel. So in our number 2, let H is a set which consists of these elements, BC, I contains 3, 5, J contains 2, 5, and K contains C. So these exercises will answer by you, class. So class, please go here and answer it. Now, let's check if your answers are correct, class. 1A, each cross I contains mark KJ, mark Fer, Joy KJ, Joy Fer. So, it's correct, class. So, in our letter B, H cross J cross I. So, mark KJ Daniel, mark Per Daniel, Joy Daniel, KJ, R Daniel, Fer. So, correct, class. In our letter C, so H cross I union H cross J contains mark KJ, mark Fer, Joy KJ, Joy Fer, mark Daniel, Joy Daniel. So, correct. So, in our number 2, so H cross I minus H cross J. Let's answer first H cross I. So, H cross I is B3, B5. Check. C3, C5 minus H cross J. So, H cross J, B2, B5, C2, C5. So, if we get the difference of this H cross I and H cross J, we get B3 and C3. So, because we cancel B5 and C5. Because in H cross I, it is B5 and C5 the same as with H cross J. So, correct? In our letter B, so H cross quantity of I intersection of J. So, BC, so H is BC. And the intersection of I and J is 5. BC cross 5 is B5 and C5. So, letter B is correct. So, in our letter C, so we have an empty set here. So, our answer is an empty set. So, type of relations. Number 1, universal relation. So, the universal relation on A is the relation A cross A. So, in our empty relation, the empty relation on any set is denoted by this set, empty set. So, number 3, identity relation. On set A, the identity relation is given by this. The set of A, comma A such that A is an element of set A. So, in our inverse relation, number 4, the inverse of any relation on set A is denoted by this. The inverse of the set B comma A such that A comma B is an element of R. So, in our number 5, composite relation of S is the set of A comma C such that there exists an element of B to R which A comma B is an element of R and B comma C is an element of S. So next is reflexive relation. A relation R on set A is called reflexive if for every element A is an element of A. So in other words, for all A comma A must be an element of R. So let's have an example. So A is a set consists these elements 1, 2, 3, 4. So now we are going to have reflexive relation. At A, which consists of these elements 1, 2, 3, 4. So in finding reflexive relation or giving an example, so R1 relations which consists of these all ordered pairs. R1 contains 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, and 4, 4. So, relation R1 is irreflexive because it contains all ordered pairs of the form A, comma A. So, for every element, A is an element of set A. R1 has 1, 1, 2, 2, 3, 3, and 4, 4. So, let's proceed on our symmetric relation. If A, comma B belongs to R is true, and then B, comma A belongs to R must be true. So in other words, R on set A is symmetric if for all A, for all B, A, comma B is an element of R, implies B, comma A is an element of R. So let's have an example. So in the set A consists of these elements 1, 2, 3. R1 contains 1, 2, 2, 1, 3, 1, 1, 3. So R1 relations which consists of these all ordered pairs. So this is symmetric relation because in simply one of the ordered pair here in our R1 must have inverse. So 1, 2, 2, 1, 3, 1, 1, 3. Let's proceed on antisymmetric relation. A relation R on set A is called antisymmetric if all A for all B, A, comma B is an element of R, and B, comma A is an element of R. Implies A is equals to B. So let's have an example. So in our set A, which consists of these elements, 1, 2, 3. R2 relations consist of these all ordered pairs. So R2 contains 1, 1, 2, 2, 3, 1. Simply one of the ordered pair here in our antisymmetric relation must have no inverse. So for example, 1, 1, 2, 2, and 3, 1. So if 3, 1 have an inverse 1, 3, then it is not unsymmetric relation. Then it is now asymmetric relation. So now, let's proceed on our transitive relation. A relation R on set A is transitive if whenever A, RB, and B are C, then A are C, that is A, comma B, B, comma C is an element of R. Then A, comma C is an element of R. So let's have an example. So in our set A, which consists of these elements, 1, 2, 3, 4. With our R1 contains 1, 1, 1, 2, 2, 3, 1, 3, and 4, 4. 1, 1, 1, 2, and 2, 3, then 1, 3, and 4, 4. So that R1 is a transitive. So in our R2 contains 1, 3, and 2, 1. So it is not a transitive because it must contain 2, 3. So it is equivalence relations if a relation is reflexive, symmetric, and transitive. So while in partial ordering, reflexive, antisymmetric, and transitive. R1 will be answered by Ms. Ryle. R2 will be answered by Mr. John. In composite of relation, R1 will be answered by Ms. Jane and number 2 is answered by Ms. Chan. Now, let's see if your answer are correct. So in our R1, so antisymmetric and transitive. Check. So in our R2, so 5, 5, 5, 6, 6, 5, 6, 6, 7, 7, 8, 8. So reflexive 5, 5, 6, 6, 7, 7, 8, 8. Symmetric 5, 5, 5, 6. So we have 6, 5. And transitive, so 5, 5, 5, 6, 6, 5. So, correct. If reflexive, symmetric, and transitive, then it is a equivalence relation. So, in our book, A is a set of these elements. 1, 2, 3, 4. So, in our number 1, we need to find R1 of R2. So, let's check. R1, R2. If we have same ordered pairs, we need to cancel it. So, R1 of R2 contains 1, 1, 1, 2, 2, 3, 1, 3, 4, 4. So, check. So, in R2 of R3, 1, 2, 1, 1, 1, 3, 1, 2, 2, 2, then 2, 1, 1, 2, 3. So, check. So, number 2 is correct.